Okay, welcome to the class. This is physics grade 12, course code SPH4U. And from today on, we're going to have a look at chapter 1 first. Chapter 1 is about kinematics. And there are 6 topics we're going to talk about. So in our first lesson, we're going to talk about the first 2 topics. And specifically today, we're going to have a look at the first one, motion and motion graphs. Okay, so cars drive by on the street, people walk and cycle past us. And garbage cans blow in a high wind from quiet suburbs to busy highways. Different kinds of motion happen all the time during a normal day, such as the situation here shown in figure 1. We often take this motion for granted, but we react to it instinctively. We dodge out of the way of objects flying or swerving towards us. We change our own motion to avoid hitting objects in our way to get to school on time. So kinematics is the study of motion without considering the forces that produce the motion. Whereas dynamics, which is the topic of the study in chapter 2 and 3, is the study of the causes of the motion. Understanding of kinematics and dynamics is essential in understanding motion. Okay, so in physics, the terms we use to describe motion, such as displacement, distance, speed, velocity, and acceleration, all have specific definitions and equations that connect them. We can divide the mathematical quantities we use to describe the motion of the objects into 2 categories, scalars and vectors, which we have talked about in our previous lesson, vectors and calculus, right? Note that scalars are quantities that have only a magnitude or numerical value, whereas vectors have both a magnitude and direction. So first, let's have a look at the terms position and displacement. To start, consider motion along a straight line, one-dimensional motion, such as a hockey puck sliding on a horizontal ice surface. So here, figure 2A shows what a multiple exposure image of a hockey puck in motion might look like. The dots represent evenly spaced intervals of time. The puck is moving the same distance in each interval, so the puck is moving at a constant speed. Here, we measure motion, we measure position, the distance, and the direction of an object from a reference point. As the distance from the origin on the horizontal axis to the center of the hockey puck. For one-dimensional motion, distance specifies the motion of this object. We can use the information in figure 2A to construct a graph of the puck's position as a function of time, as shown in figure 2B. Also notice that in figure 2B, the distance axis is now vertical as we plot the position vector D as a function of time, T. In such a position, the time plot, it is conventional to plot time along the horizontal axis. The change in puck's position in one direction is in its displacement. Mathematically, for one-dimensional motion, displacement is written as delta D equals D2 minus D1. Also note that delta D, D2, D1 are all vectors. Where D1 is the object's initial position and D2 is object's final position. Well, displacement tells us how far an object moves. It does not tell us how fast it moved. Vectors provide two pieces of information. So we need a specific way of presenting this information clearly and ambiguously. For example, a displacement of 15 meters east clearly identifies a magnitude of 15 and the direction of east. Okay, so next, let's have a look at another two concepts, which are called speed and velocity. Speed and velocity are related quantities, but they are not the same. Many people use them interchangeably in everyday language, but strictly speaking, this is incorrect in scientific terms. Speed tells how fast an object is moving, and speed is always a positive quantity or zero. The distance between adjacent dots in figure 2a shows how far the punk has moved during each time interval. The average speed we average of an object in total distance traveled divided by the total time to travel that distance. Speed is a scalar quantity, does not have a direction. The SI unit for speed in meters per second. So note that you can calculate the average speed using the following equation. Here, B average equals delta D over delta T. All of the three quantities are scalars. On the other hand, let's have a look at the velocity. Velocity, the change in position divided by the time interval, is a vector quantity. So it is written with the vector arrow V. The direction of V indicates the direction of the motion. In the punk example we have just discussed, the direction of the velocity is to the right, but it could have negative or even zero. Well, if it has negative value, that means a motion to the left, right? So before you describe a velocity, make sure you specify your positive direction first, okay? If you specify the right direction is a positive direction. So anything moves to the left has a negative velocity, right? So velocity can be positive, negative, or zero. So how does an object's velocity relate to its position? For a particular time interval that begins at time t1 and ends at t2, the time interval is delta t equals t2 minus t1. We can then calculate the average velocity using this equation. The average velocity, V average, equals vector delta t over vector delta d over delta t. So delta t is a scalar, delta t is a vector, and velocity average is a vector as well. So the hockey punk example in figure 2a is sliding at a constant speed. So its velocity always has a constant value, as shown here in the velocity time graph in figure 2c, as you can see there on the top. So in this case, the velocity is positive, which means the direction of the motion is towards the increasing values of delta D, which means towards the right. So when an object moves with a constant speed, the average velocity V average, the displacement divided by the time interval for that change, is constant throughout the motion. And the position time graph has a constant slope, as shown here in figure 2b. For more general cases, the average velocity is the slope of the line that connects the position at the beginning and the end of the time interval, called the secant line. This is illustrated in the hypothetical position time here in figure 3. So next, let's have a look at a tutorial 1. We'll try to solve two simple problems related to the average velocity and average speed. Okay, so consider this problem here. Sample problem 1. The jogger takes 25.1 seconds to run a total distance of 165 meters by running 140 meters east and then 25 meters west. The displacement is 115 meters east. A, can you calculate the jogger's average velocity? B, can you calculate the jogger's average speed? So be careful with the difference between the two terms, velocity and speed. Okay, now I'll give you 4 minutes to consider this question by yourself. And then we'll have a look at the solution together, okay? Make sure you have a notebook. And try to solve this question by yourself first. Let's have a look at the solution together. So in question A, we have delta D equals 115 meters east, right? And we know delta T equals 25.1 seconds. So we want to find the average velocity. According to the formula, average velocity equals average displacement delta D over delta T, right? Delta D is a vector, so we can put these values in. Delta D is 115 meters east divided by 25.1 seconds. That should give us the average velocity equals 4.58 meters per second. The direction is east. Remember that the average velocity is also a vector, right? So in addition to specify its magnitude, you should also specify its direction, which is east. So in question B, we need to calculate the average speed, right? So average speed equals the delta distance. So this time we should use the total distance this object traveled, which is 165 meters, divided by the time it used, which is 25.1 seconds. And the result is a scalar, which is 6.57 meters per second. Okay, any questions? All right, no questions. Let's have a look at another concept, which is graphical interpretation of velocity. To consider another example of y-dimensional motion here. A rocket-powered car traveling on a straight, flat road, which is shown here in figure 4a. Assume the car is initially at rest. Initially means that the car is not moving when the clock reads 0. So it's just standing there. At t equals 0, the driver turns on the rocket engine and the car begins to move forward in a straight line path. So here, in the figure 4b, this is a motion diagram shows the position of the car at evenly spaced instants in time. And accordingly, figure 4c here shows the corresponding position time graph for the car, where again, we use dot to mark the car's position at evenly spaced time intervals. Notice that the dots are not equally spaced along the position axis, right? Instead, their spacing increases as the car travels. So what does that mean? You can imagine that's a accelerated motion, right? So it's not traveling at a constant speed, but with a constant acceleration. Well, probably constant or not, but there is an acceleration there. This means that car moves further during each successive and equal time interval. So the velocity of the car increases with time. In this example, the car moves toward increasing values of position. So the velocity is again positive and increases smoothly with time, as shown here in figure D. This is the graphical interpretation of the velocity. Okay, so next, let's have a look at a concept called instantaneous velocity. Also, we have talked about this concept in the calculus and vectors class, right? So have a look at these two figures, figure 5a and b. This is position time graph for an object moving a certain displacement over a short time period, right? Again, we can use dot to mark the position at the beginning and the end of the particular time interval, which starts at t equals 1.0 seconds and ends at t equals 2.0 seconds. The average velocity during this time interval is just displacement during the interval divided by the length of the time interval, right? Figure A shows that this average velocity is the slope of the secant connecting the 2 points on the curve. Remember, we have learned two concepts. One of them is average velocity, right? In our previous class, calculus and vectors. Whereas we can also have a concept of instantaneous velocity, which is once the interval is very small, the limit of the secant line approaches the slope of the tangent line, right? The slope of the tangent line is actually the instantaneous rate of change, which is in physics, in this context, means instantaneous velocity. So with this approach, though, we lose the detail about what happens in the middle of the interval. If you want only finds an average velocity, you will end up like this, right? In figure 5a, the slope of the position time curve varies considerably as we move through the interval from t equals 1 to t equals 2. If we want to get a more accurate description of the object's motion at a particular instant within the time interval, say, for example, t equals 1.5, it's better to use a smaller interval. So the question is, how small an interval should we use? In figure 5b, as you can see here, we can consider slopes over a succession of smaller time intervals. So intuitively, we expect that using a smaller interval will give a better measure of the motion at a particular instant in time, right? So from figure 5b, we see that as we take smaller and smaller time intervals, we are actually approximating the slope of a position time curve at the point of intercept t equals 1.5 seconds using a tangent line. A tangent line is a straight line that intersects a curve at a point and has the same slope at the curve at a point of intersection. The slope of a tangent to a position time curve is called instantaneous velocity, which is denoted by vector v, which is the velocity of an object at a certain instant of time. In some cases, a moving object changes its speed during its motion. So we need to clarify the difference between the average speed and instantaneous speed as well. As mentioned earlier in this section, average speed is the total distance divided by the total time. Instantaneous speed, v, refers to the speed of an object at given time instant in time and is defined as the magnitude of the slope of the tangent to a position time graph. Moving objects do not always travel with changing speeds. Objects often move at a steady rate with a constant speed. The difference between the average and instantaneous values could be understood using the analogy of a car's speedometer. The speedometer reading gives your instantaneous speed, which is the magnitude of your instantaneous velocity at a particular moment in time. If we are taking a long drive, our average speed will generally be different because the average value will include periods when we are stopped in traffic, accelerating to pass the other cars, and so on. In many cases, such as in discussion with a police officer, the instantaneous value will be of greater interest. So the instantaneous velocity gives a mathematically precise measure of how the position is changing at a particular moment, making it much more useful than the average velocity. For this reason, from now on, in our lesson, we refer to the instantaneous velocity as simply the velocity, okay? So if not specified, when you see the word velocity, this means instantaneous velocity. Otherwise, it will tell you that's an average velocity, okay? Okay, next let's consider another tutorial which consists one question. showing how we can work with motion graphs. Okay, so let's consider this sample problem here. The position time graph in figure 6 shows the details of how an object moved. There are two questions. Question A, calculate the average velocity during the time interval from t1 equals 1 second to t2 equals 2.5 seconds. And question B, analyze the position time graph in figure 6. Use your analysis to sketch a qualitative velocity time graph of the object's motion. Okay, now I'll give you 5 minutes to have a look at this question by yourself.
老师，你静音了。
Oh, sorry. Okay, let's have a look at the question A again. So in question A, we want to find the average velocity. Average velocity is calculated using difference between the two displacements over delta t. So put all the values in, you can see that the average velocity is 1.3 meters per second. Okay, so this is just a one type of notation. You can use another type of notation. For example, at the very beginning, you should specify which is your positive direction. For example, in this example, we can choose the right direction is your positive direction. That in this settings, D2 must be positive and D1 is also positive, right? And if the average velocity is 1.3 meters per second, then we know the direction of the average velocity is to the right. So you don't have to specify the direction like this. Again, this is just two types of notations. Okay, you can choose either one you like. If don't specify the direction in the parentheses at the back of your magnitude, you have to specify which direction is your positive direction at the very beginning of your solution. Okay, if you don't do that, you have to specify the direction of each of the vectors you use, because remember, vectors have both magnitude and direction. Okay, so for question A, we can state that the average velocity during the time interval T1 and T2 is 1.3 meters per second. Direction is to the right. And in question B, we want to estimate a position time slope at these places and then construct a qualitative velocity time graph. So first, we can generate the data for the velocity time graph, analyze the motion of the object in figure 6. This object is initially moving to the right. The object reverses direction near 2.5 seconds and 4.0 seconds. So at time T1, the slope is large and positive. So V is large and positive at T1. At T2, slope is approximately 0. So V is near 0. And then between T2 and T3, the object is moving towards small values of positions. So the slope of the position time curve, and hence the velocity are negative. At time T3, the slope is 0, so the velocity is 0. Finally, at T4, the object is again moving to the right because D is increasing with time, right? So V is again positive. So from this analysis, we can construct a qualitative velocity time graph. Again, because it's a qualitative velocity time graph, it does not have to be very accurate. As long as the trend is correct, will be fine. Okay. Any questions? Okay, so remember the average velocity is the slope of a secant on the position time graph. To analyze the velocity, usually we take approximate values by drawing lines tangent to the position time curve at several places, then calculate their slopes. The instantaneous velocity at a particular time is always equal to the slope of the position time curve at that time. Okay, next, if you don't have any questions, let's consider the concept of acceleration. Acceleration is a measure of how velocity changes with time, right? The SI unit for acceleration is meters per second squared. Sometimes objects move at a constant velocity, but usually the velocities we observe are changing. When an object's velocity is changing, that object is accelerating. We can study acceleration using velocity time graphs. These graphs display time values on the horizontal axis. and the velocity on the vertical axis. Velocity time graph can be useful when studying objects moving with uniform or constant velocity or uniform acceleration. So velocity time graphs for both uniform velocity and uniform acceleration are always straight lines. By contrast, the position time graph of an accelerated motion is curved. Also remember, in the calculus and vectors class, we have studied that velocity is actually the first derivative of the displacement function, right? And acceleration is actually the second derivative of the displacement function, or the first derivative of the velocity function. When an object's velocity changes by delta v over time delta t, the average velocity A, average, or the change in velocity divided by the time interval for that change during this interval, is given by the following formula. A average equals delta v over delta t. This is only for average, okay? So for instantaneous acceleration, we have already learned this as I said, we have already learned this instantaneous acceleration. That's the second derivative of the displacement function with respect to time, right? Okay, now let's consider an exercise here. Suppose the sprinter in figure 9a is running a 100-meter dash. The sprinter's time and distance data have been recorded and used to make the velocity time graph in figure 9b. Okay, so note that this figure is a velocity versus time figure. The trend of velocity with respect to time. And there are two questions. A, analyze the velocity time graph in figure 9b. Use your analysis to make a sketch of an acceleration time graph of the sprinter's motion. Question B, from your acceleration time graph, determine the maximum acceleration at the time at which it occurs. Okay, again, I'll give you 5 minutes to consider this question by yourself first, and then we'll have a look at the solution together. Okay, have you finished? Yep, let's have a look at the solution together. Okay, question A. Acceleration is the slope of the velocity time graph, right? Because acceleration is the first derivative of velocity with respect to time. So first, we must estimate this slope at several different values of t to be able to graph the sprinter's acceleration as a function of time. So figure 9b shows several lines tangent to the velocity time curve at various times. The slopes of these tangent lines give the acceleration. Estimate the slopes. Then use the slope estimations to sketch the acceleration time graph. The resulting acceleration time graph is only qualitative here, not that accurate, okay? So more accurate results would be possible if we had started with a more detailed graph of the velocity. So far, we can only have an approximate acceleration time graph like this, shown here on the graph on bottom right. Okay, as to question B. From this graph, we know that the largest value of the acceleration is approximately 11 meters per square second. This occurs near the start of the race, around t equals 1.5 seconds, when the sprinter is gaining speed. Also note that this is where the slope of the velocity time graph is largest. At the end of the race, though, as the runner crosses finish line, he slows down and eventually comes to a stop with speed equals 0. Okay, so this is the first half of chapter 1, lesson 1. Remember to have a look at the homework, which is on Google Classroom. I'll also upload today's lecture slides to Google Classroom as we did in our previous lessons, okay?